Hello, are you able to see the presentation?
Yes, sir.
Okay. All right, so we're going to start. So we have started with Coulomb damping, and yesterday we discussed about Coulomb damping. All of you have received the lecture questions and the quiz, right? Gaurav?
Yes, sir.
Okay. Is there any disturbance in audio?
No, no, sir.
Oh, okay. All right. So we have already started with the Coulomb damping, and Coulomb damping is due to dry friction. And we solved for this Coulomb damping. We derived the governing differential equation for that, and we have stated some assumptions. And the main assumption was we're assuming that the mass is placed at the extreme RHS position of the mean equilibrium position, and it is released from rest. Okay, so the initial velocity is zero. Initial displacement is uh, the position from this mean equilibrium, extreme position from the mean equilibrium position. All right, and the motion we analyze the motion in two half. In first half, the mass is moving from right to left, and we derived the governing differential equation for that, and we solved. And the govern now for the one half of the cycle, that is from 0 to pi by omega n, 0 to pi by omega n, the system oscillates about this axis. X is equal to f by k. And okay, and this is the solution for that. This is SHM standard solution. We solved for the solution using the boundary conditions. These are the boundary condition. X at t is equal to 0 is x0. That is the initial displacement. That is the extreme position. And x dot at t is equal to 0 is 0. That is the velocity at t is equal to 0 is 0. That is the mass starts from rest, and we derived the equation. So the governing differential equation for one half of the cycle, that is 0 to pi by time is from 0 to pi by omega n, is x minus f by k is equal to x0 minus f by k into cos omega n. All right. So this is for one half of the cycle. Similarly, we derived now using that we derived this displacement when t is equal to pi by omega n. That is when the when the mass is at one half end of the cycle. Okay, so we deduced the displacement at t is equal to pi by omega n, and it was minus x0 minus 2f by k. All right, and this is important because this becomes one of the boundary conditions when we solve for the next half of the cycle. All right. So in the next half of the cycle, the mass moves from left to right. Again, we solved for the governing differential equation. Only difference is that the direction of friction is now reversed. We got the governing differential equation. Then we uh, again now here uh, the SHM will be about the axis x is equal to minus f by k. Okay, so here it will be about the axis x is equal to minus f by k, and when we plot it, it looks something like this. And the governing differential equation solution now is y is equal to a2 cos omega n2 plus b2 sin omega n2. All right, and y is nothing but x plus f by k, and this is again we applied the boundary conditions and solved for it and found out a2 and b2. Okay, now this is for the cycle from pi by omega n to twice pi by omega n. All right, and the one of the boundary conditions we got it uh, from the one half of the cycle, that is for t is equal to pi by omega n, the displacement is minus x0 minus 2f by k, and then the second boundary condition becomes x dot, that is the velocity at t is equal to pi by omega n, is equal to 0 because it is an extreme position. All right, so velocity at extreme positions will be 0. We substituted we substituted these boundary conditions, and we found out the constants a2 and b2. All right, so a2 is x0 minus 3f by k, and b2 is 0. Right, again because it is an extreme position. Right, and so our for second half of the cycle, the equation becomes x plus f by k is equal to x0 minus 3f by k cos omega n. Okay, now substitute. Now we have to find out the amplitude at the end of the cycle. So that is named as x1. So that is after t is equal to twice pi by omega n. So substitute t is equal to twice pi by omega n in the equation, and from that we get x1 is equal to x0 minus 4f by k. Alright. So based on that, F is equal to nu n, that is the frictional force, and so decrease in amplitude at the end of the cycle, that is x0. So if you see the cycle, this is your cycle, and this is one cycle. So this is x0, and this is x1. All right. So x0 minus x1 is nothing but 4f by k. So this is how much the amplitude of the decreases at the end of the cycle, at the end of one cycle. All right. So this was just a recap of what we have done yesterday, and since it is mathematically quite intense, so I thought it would be a good idea before starting today's lecture, just do a quick recap, and based on whatever has discussed, open up your quiz and answer these questions. Okay, you can submit the answers. Okay, you can submit the answers multiple time, but only the first submission will be considered, okay, as per the timestamp. All right. So for today's quiz, you can submit the answers for the quiz multiple times, but only the first submission to the quiz will be considered. So go ahead, open up your quiz, and these are the 6 questions. So in the 6 questions, you will find answer them in the sequence in your form.
Sir, can we submit all together in the end?
If you want, you can submit it all together in the end, but no extra time will be provided at the end. Okay, at the end, at the end, I will be closing the quiz at 12 o'clock. So that is up to you.
Okay, sir.
No, actually, don't submit it at the end. I am giving you 5 minutes. So it is approximately. Okay, so at the end will not be allowed.
Sir, after the first question, when we want to submit for the second question, we only have to fill in the second one, right?
Yes, or you can fill in, so enter the solution for all the 6 and then simultaneously. That will be a better way to do it. It is up to you anyway. Okay, so I am the time stamp is 10:28. So these are all true and false questions. So I guess 5 minutes should be enough. So I will close. You have till 10:33. So if in the timestamp, if your solution, if your response is at the end, then that will not be considered. Okay, so it should be around this timestamp. Okay, one minute here and there will be okay, but it should be around. No, it cannot be around. So it is 10:20 to 11:20. So your answer for this question cannot be at 11:20. The timestamp will, if the timestamp is at 11:20, then those answers will be given 0 marks. All right. So you have to submit it within this time frame itself.
Sir, we can't see the question because of your
Just a
phone
minute,
tap.
just a minute. Okay.
So after this 6 questions, we have to submit the form, right?
Yes.
Thank
After you make your choices, just click on the submit button. All right. So the time your answer is recorded at that particular timestamp. And you can see, even if you make multiple submissions, only the first submission will be considered. So be careful while you submit. All right. I hope that is clear. The first submission as per the timestamp will be considered. So even if you are submitting the answer again and the second time it is correct, it will not be considered. All right, time is up. Submit your answers. All right, I have seen 0 responses. Submit your responses, otherwise your response will not be considered.
So we have submitted the response.
Yes, sir. I also submitted.
Yes, sir.
Accepted
Yes,
once again.
sir. Yes, sir.
Okay, okay, yeah, I have seen the response. Just needed a refresh. Okay, so we will continue. Okay, anything beyond outside of this time frame of the timestamp will not be considered. So accordingly, all right. So we have studied the entire cycle. So like a little bit of we should do a little bit of more critical analysis of this complete cycle. So we'll study how the system behaves when a mass is under Coulomb damping. All right, and we'll see what are the salient features and how it differs from viscous damping. All right. Okay. Now, if you see this graph, the one half of the cycle, say suppose, so this is the entire motion is analyzed over a period of twice pi by omega n. All right. So this is 2 pi by omega n, and half of that is pi by omega n. All right. So now for the first half, that is from 0 to pi by omega n, the motion is about axis. Please pay attention to all these details, because the next quiz question will be based on all the discussions which we are having currently. All right. So don't make sure you understand everything that is being discussed now. All right. So this distance from the axis is nu n by. All right. Now for the cycle from pi by omega n to twice pi omega n, the cycle, the remaining of the cycle is centered around all right, is centered around. So this distance is again nu n by k, and just to be accurate, it is actually negative, minus nu n by k, because it is below the axis, that is your horizontal x axis, that is the time axis. Okay. So on x axis your time, y axis you have displacement, and initial displacement is x0, that is the initial position to which the mass is moved. Right. So the mass is initially from the mean equilibrium position, it is stretched and placed at this extreme position. So this is the initial position of the mass, and this is your x0. All right. And then it goes from x0 to other side. So on the other side, so that is, so this is x0, and if I say let's mark this as x bar. Okay, so this is your, this will be your distance x bar. All right. And then it again comes back, and this will be x1. All right. So in this final, so during each half of the cycle we have saw that the amplitude goes on decreasing, and during each of the half of the cycle the amplitude decreases by 4 f by k. All right. So here the amplitude is going to decrease by 4 f by k, and again here again in the second half the amplitude is going to decrease by 4 f by k. So x0 minus x1 is 4 f by k. Right. So that is what we have deduced. Okay. Now if you see the decrease in amplitude from x0 to x1 and to the next cycle, the decrease in amplitude is linear. All right. The amplitude decrease in the successive cycle is by a constant amount, that is 4 f by k. All right. So x2 minus x1 also will be 4 f by k, which is different from what you have studied in your what you say, the viscous damping. Okay. Under damped system with viscous damping, decrease is for under damped with viscous damping, the decrease is not uniform. So in that case the amplitude is constant. So in that case x0 by x1 will be equal to x1 by x2 and so on, and that we are calling it as the logarithmic decrement. All right. So please note the difference between those two. In this case the difference in the amplitude of successive vibration is constant. In this case the ratio of the successive amplitude remains constant, and that is called as the logarithmic decrement. All right. So this is the one of the key difference between the two types of damping. All right. All right. Now, if I draw a horizontal line somewhere over here, and if I take a tan theta of this, right? If I take a tan theta of this, all right. So tan theta. So vertical distance is this one. This is your vertical distance. So that is nothing but x0 minus x1. So that is nothing but 4f by k, right? That is the numerator. Okay, so this distance is 4f by k, all right, and the adjacent side is nothing but the time interval. So that is the twice pi by omega n, all right, that is the time axis. So the rate of decrease in amplitude will be given as tan theta, that is the slope, and that comes out to be 4f by k divided by twice pi by omega n, and that comes out to be 2 nu n omega n divided by pi, all right. And since the slope is negative, then this negative sign is applied to it, all right. So this is how the amplitude decreases. So these are some of the key features. Make sure you note all the things, especially the equation, all right, because some quiz questions can be asked on this, all right. So this is the rate of decrease of amplitude, all right. Now, any questions in this? Is the graph clearly understood? All right, so I am assuming everybody must have followed. So now go to your next set of quiz question. So answer whatever we have discussed just now. Answer quiz question number 7, 8, and 9. Okay. Again, I am going to give you 5 minutes for this. So the time stamp will be from 10:43 to 10:48. All right. So the data is given for an underdamped system with Coulomb damping. The frictional force is 2n, stiffness is 1 Newton per meter, omega n is pi. Then find out the rate of decrease of amplitude. Take coefficient of friction as 0.5. Right. Again, submit the answers without units. You have to answer for the units in question number 8. Okay, so question number 8 you have to state the units. Question number 7 you have to just state the value.
Sir, in
Yes.
question number 8, what is it written? I cannot understand. The rate of
एक minute. It is the rate of decrease in amplitude. Is it clear now? Somebody asked clarification? Is it clear? Person you just asked.
Yes, sir. Yes, sir.
Okay. After
So,
yes,
so in the question number 7, do we have to write the answer with the sign?
that you decide. What
Okay,
has
sir.
been just discussed now. Accordingly, you decide.
Okay.
So select, make your choice and submit it.
Sir, the ninth question you show later, no?
Yes. 9 question. So for same data as question number 7, the decrease in amplitude per cycle is, you have to find out. Yeah, you have 1 more minute to submit your answer.
Sir, can you just show the question 7 again? Okay.
You have 1 more minute to finish the quiz.
So can you show 8th question? Previous slide. Hello, sir.
Hello, yeah, it is on the screen. All right, time is up. Please submit your answers. Time is 8:48. Beyond 8:48, sorry, 10:48. Beyond 10:48, answers won't be accepted. Submit your answers fast.
Sir, question 9.
All right, I'm now. Yes, submit your answers.
Hello, sir.
Yes.
Sir, at the beginning, my PC gets hanged, due to which I am not able to answer the question 1 to 7. Can I have some time? Hello.
Okay, okay, submit it, submit it. You are not submitted 1 to 7.
No, no, means not because of time, but my PC gets hanged. Beginning to that question. Later on, after means lots.
Okay,
Later on, it.
Who is that Sudarshan Gawande?
Yes, 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 sir.
Okay. All right. I will make a note of that. Submit your answer.
Okay.
All right. So let's continue. So far, in the earlier discussion, we did a complete detailed analysis for the entire cycle of the mass and how the amplitude varies from one half of the cycle to another half of the cycle. Now, if I want to derive how much is the decrease in amplitude of the mass, I can use another method, right? So, mass, all right, and you have your mean equilibrium position. This is the mean equilibrium position. And the mass is initially at the extreme right. Alright. So this is your x0. Initially the mass is at x0, then it is released, then it goes on the left hand side and it is at a distance of x1 bar, x bar. Alright, then again it returns to its original position. So this is position 1, this is 2, and from 2 again it goes on the right hand side of the mean equilibrium position. Again goes here. Alright, and this is position 3, and at this distance of the mass is x1. Alright, okay. So what I'm going to do, so I'm going to divide this whole motion into two halves. So first half is from 1 to 2. Alright, and instead of using our D'Alembert's principle, I am going to use the work energy principle. I hope you are familiar with the work energy principle that we studied in first year. So work energy principle says that work done is equal to change in kinetic energy. Alright, that is equal to T2 minus T1. Alright, so spring work, this is all spring work, so that will be half K into x0 square minus x1 bar square minus F, frictional force F, into x0 plus x1 bar, that is the force, frictional force into displacement, and kinetic energy at T1 and T2 both are equal to 0. Alright, so if I simplify this, I get x0 minus x1 bar is equal to 2F by K. Now let's analyze the motion from 2 to 3. Okay, so from 2 to 3. Okay, so 2 to 3. Alright, so again work done is change in kinetic energy. So that will be half K into x1 bar square minus x1 square is minus F into x1 bar plus x1 is equal to 0. Alright. And again I can simplify that, x1 bar minus x1 bar minus x1 is equal to 2F by K. Alright. So now I have two equations. Equation 1 is x0 minus x1 is equal to 2F by K, and x1 bar minus x1 is equal to 2F by K. So add 1 and 2, so I get x0 minus x1 is equal to 4F by K. That is the decrease in amplitude of the cycle, decrease in amplitude per cycle. Alright, so you can derive this part by using the work energy principle also, but this will give you only the end result, that is the decrease in amplitude. But how the system behaves throughout this cycle intermediately, For that, the detailed analysis is required. All right. Okay. All right. So we'll do some numericals on this. I hope everybody has the question sheet with them. So I will just read the question. A single degree of freedom system consists of a mass 20 kgs, spring of stiffness 4000 Newton per meter, and amplitude of successive cycles to be found to be as 50, 45, 40, and 35, and so on. Determine the nature and magnitude of the damping force. Also find the frequency of damp vibration. Okay. We solve this question. Right. So if you see the first part, the nature of damping. Okay. So if you see the decrease in amplitude is by a constant amount. All right. So if the decrease in amplitude is a constant amount, then the type of damping is decrease is constant. So type of damping is Coulomb damping. If the ratio is constant, then it is viscous damping. Okay, and this decrease del, or you can write it as del, is 4F by K. All right. So del is how much? Del is 5 mm. Okay, if you see the data, it is, see, 50 minus 45 is 5, 45 minus 40 is 5, 40 minus 35 is 5, so it is constant, so it is 5. Okay, and it is in mm, so convert this into meter. So 5 divided by 1000 is equal to 4 into F divided by K, that is 4000. Alright, so F, that is equal to damping force, is equal to 5 newtons, and natural frequency omega n is equal to square root of K by M. Alright, so that comes out to be 14.14 radians per second. I hope that is clear. Any questions, please ask. Alright, moving on. Okay, so this is the calculation. Moving on. So next question.
Sir,
Yes.
sir, damping force and the frictional force are the same, na?
Yes.
Okay, okay, sir.
Frictional force is the damping force. Alright. Next question. A vertical spring has a mass of 0.5 kgs and initial deflection is 2 mm. Find the spring stiffness and natural frequency of the system if subjected to Coulomb damping when displaced by 20 mm from the equilibrium position. All right. So the same strain, initially it is vertical, okay, and initial deflection is given as 2 mm. Now the spring is subjected to Coulomb damping, and it is initial displacement is 20 mm from the equilibrium position, and it is released and it undergoes 10 cycles and comes to rest in the extreme position on the side on which it is displaced. All right. So here it was a mass, okay, it was displaced on the right. This is the mean equilibrium position, and it was displaced. Suppose it was displaced on the right hand side, then it comes to rest on the same side. Okay. So that means what? The cycle is
Hello.
So you are inaudible.
Hello, Gaurav, are you able to hear me?
Yes, sir.
Or dropped because of the power failure, the net was disconnected. Okay, are you able to, everybody is able to see me now?
Yes, sir.
Gaurav? Okay, 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 we'll continue. All right. So the mass is on the same side of the equilibrium position. Okay. So you have to calculate the Coulomb damping and find the rest position. That is the question. All right. We'll solve this question. All right. So it is given that m is equal to 0.5 kg. All right. So delta static is 2 mm. All right. So omega n is equal to root of g divided by delta static. All right. So use the initial part of the data to find the natural frequency. So that comes out to be 70.04 radians per second, and that is same as square root of k by m. All right. So you know m is 0.5 kg. So using that you will get the value of stiffness. So that comes out to be 2452.5 Newton per meter. All right. Now del is 4f by k, that is decrease in amplitude per cycle. All right. Now when the mass comes to rest, so that is an equilibrium. All right. Equilibrium. So why does the mass comes to rest? Because the frictional force at that instant matches with the spring force. All right. As the amplitude of vibration goes on decreasing, the spring force also will goes on decreasing, and finally it reaches a stage there where the spring force is balanced by the frictional force, and when that happens, the mass is unable to overcome the frictional force and it will stop. All right. Now F is equal to K into XF, where XF is the final position. Right? XF is the final position. Now del, that is the decrease in amplitude, is 4 K into xf by k. So that is nothing but 4 times xf. Right? So decrease in amplitude is x. Right? Now number of cycles the mass will undergo. Number of cycles the mass undergoes is equal to 10. All right. Now x max is given as 20 mm. All right. So x final will be x max minus number of cycles n into the decrease in amplitude per cycle. All right. So x final becomes 20 minus 10 into 4 times xf. That is what we found out in the earlier equation, this equation. All right. So del we have found out in terms of xf. So no, bring everything to this on one side. So that gives me xf is equal to 0.488 millimeters. All right. Or that is equal to 0.488 into 10 raised to minus 3 meters. All right. So this is the final rest position. Okay. Right. Now damping force F is equal to x into x k into xf, and that comes out to be 1.196 meters. All right. All right. Okay. So that's all for today. I will take the attendance, and this also completes the. Yes, go on. Somebody has a question. That
Sir, may I
completes.
submit now?
Yes, submit. That also completes the, what do you say, the second module.
Hello, sir.
Yes.
Can you open the form for just 1 second? I want to submit it.
It is open.
Okay.
I will just download the
Okay,
attendance.
sir.
Let me just copy it. Have you got the message regarding today's practical?
Sir,
Yes,
today
sir.
for B1 it will be heat transfer and B2 it will be MSTD, right?
No, not MSTD. The MSTD batch is going to have the DOM practical. See, you are now you are divided according to your what do you say? According to your electives, right?
No, sir.
No. See.
So previously we were divided according to our roll numbers by Avadut sir.
No, not that. See,
Yeah.
you are attending lectures according to your elective.
So you mean both divisions combined or separately?
Not both divisions combined. For your class.
Sir, currently the entire B division is attending your lecture. But for the elective, you have to
let me
separate.
just
Yeah.
download that.
It means the MSCD students in B division will be in B1.
Not B1. I think it is B2. Wait a minute, let me just open the message and check.
B1.
Let me just complete the download thing first, because I tend to forget. Alright, now let me open the WhatsApp message. or I sent you the message, right, on the Teams. What was that?
Sir, could you please update the PPTs as well on the portal?
Yeah, I think couple of them are remaining, last 2 lectures. Rest
Yes,
of
sir.
them have been updated.
Yeah.
For only 14 and 15 are
Yes,
remaining
yes,
because
sir. 14 and 15 are remaining. Yeah.
correct. Okay. Okay, so B2 batch is so all students were who have MSTD as their elective. Okay, they are B2 batch. Is that clear?
So majority of students have taken PTD as their elective.
See, that doesn't matter.
Only,
That
oh,
doesn't matter. Okay, because there has to be it is required to maintain some uniformity, na, in the practicals. You have practicals for PTD and MSTD also, right?
Yes, sir.
yes, sir.
So if everything is mixed, then uniformity cannot be maintained. So B2 batch is all the students with MSTD. Okay, B1 batch is all the students with what is your other elective?
PTD.
PTD. Okay, so
Yes,
today
sir.
for B2 batch will comprise of all the students who has taken MSTD as their elective. Okay, so other students should not join the. See, right now the separate team for B2 and B1 batch has not been created. So what I have done, I have scheduled the DOM practical for the entire class. That doesn't mean the entire class have to attend the DOM practical. Only the MSTD students that are in B2 batch have to attend the DOM practical. Is that clear? Rest of the B1,
Yes, sir.
rest of the students have to attend the other practical.
Sir, so it is not like that the serial number 1 to 36.
It is not like that. The batches for practical are not as per your roll number. Because okay, is that clear to all? Who is
Yes,
supposed
sir.
to attend the DOM practical today?
Yes, yes.
Okay. So in today's DOM practical, we will be doing the experiment on simple and compound pendulum. Okay. So the lecture will be demonstrated to you in the form of video, and you have to what do you say record all your readings. So first, initially you record it in your rough, make a rough journal. All right, and in that rough journal you record all your readings, do the calculations, and submit it at the end of the practical. All right, just take a photograph and submit it. Now many students yesterday were complaining about there is no cam scanner is now not available. So there is no soft, but if even if cam scanner is not available, there are, if you just type in your what do you say that Play Store, Google Play Store, just type PDF Maker, you will get several software. Okay, that one of the software is PDFO. It is called as PDFO. That is very good. I tried that. So using that software, you submit your work, lab work. All right, prepare a PDF and submit it. Okay, so this is what we are going to do today. Okay, now when you have your next practical, then what you have to do is you have to submit it in the fair. So to submit it in the fair, I will give you the manual. You have to either take a printout of that manual or take a Xerox, whatever is convenient to you. Okay, right now it will be printout. So take a printout of that manual, and all the calculations in that have to be filled manually, not typed. Okay, with pen and pencil, you have to fill and make sure that you preserve that report. Okay, the reason why I'm telling you is that right now we are in online mode, but if there are some changes, suddenly we might start that there might be offline mode also, and then you will be required to submit the journals. Okay, so whatever written work, like either assignments or experiments, whatever reports you prepare, you have to prepare handwritten reports, okay, and then you have to send the scanned copies, and make sure you preserve both your assignments and your handwritten reports. Is that clear to all? All right. So I hope that is clear. I am going to end the lecture now. Time is up. Any questions? Please ask me quickly. Or if we have no questions, I have already downloaded the attendance. I will just stop the recording and you can leave.